All right, so is the screen visible for everyone?
Yes.
Okay, so first of all, welcome back. Hopefully everyone had a great Eid. And so I think we were doing displacement time graphs, right, last time. We finished displacement time graphs. We also had a quiz, and I went through some of your quizzes, and they were good. So I'll share. Once I check all of them, I'll share all the quizzes back with you. And if you have any question regarding quizzes, we can discuss those when I share the quizzes with you. Yeah. Is there any question from the last class that we did? From displacement time graphs or graphs in general? Any question? Okay, there's no question. All right, so the topic that we'll be starting today is velocity time graphs, and we'll try to cover the topics quickly now, as I have received some feedback that we can increase the speed of our lectures as well. So, all right, so okay, so velocity time graphs are giving you a relationship between velocity and time, right? Obviously. So they'll tell you what that means is that how does the speed or velocity of an object changes as time progresses further. So it, of course, again, we have a time on the horizontal axis and velocity is plotted at the vertical axis. So, for example, you could have a graph that looks like this. Now, the ideas are still similar to what we discussed in displacement time graph. We'll see how do we apply the same ideas in this thing. So for example, if this is velocity and this is time, what is this graph telling you about velocity of the object? Anyone? Okay, so it's really telling you that if you look at time intervals, at every time interval, you can see that the velocity remained the same, right? So it's still over here. If you look at this time interval, it's still over here. So this is a graph that shows you that the velocity was constant all along. So this is representing constant velocity. Now, again, we can have a graph that looks like this, where we'll also introduce the concept of slopes for velocity time graphs, where suppose that you have a line that looks like this. You can see that it's a linear line. That means it's a straight line with no bends, right? So if a line looks linear in this way, then what is this telling you? This is telling you, if you look at every time interval, so suppose that this is the time at this point, and at this time you have some velocity like this. So you can label them in the same way we did for displacement time graphs, T1, T2, and for T1, you corresponds to velocity, some velocity, you can call it V1, and at T2, it corresponds to some velocity, you can call it V2. You can clearly see that V2 is greater than V1, right? This arrow that I've represented, this line axis is pointing upwards, means that the values are increasing in the upwards direction. I'm sure you all already know that. So if velocity V2 is greater than V1, I can compute the slope of this line as well. And we know that the slope of this line is going to be the change in velocity divided by the change occurred in time, right? To cause that change in the change in time for how long did it took to change the velocity, right? So what is this? delta v by delta t, change in velocity by change in time, we know that we have already seen that this is known as the acceleration of the object, right? So if there is some positive change in velocity as time moves forward, then that means that the object has accelerated due to some force that had acted on the system or on the object. So this means that the slope of velocity time graphs gives you accelerations. And suppose in this case, if you have a slope like this, you can see that the ratio of velocity to time at every point is same, right? So if I took this point or this point and I computed, suppose this is v3 and this is v4 corresponding to some t3 and t4, I'd compute the slope in the same way and I'll still get the same value for acceleration, whatever value this a is. So this means that this slope represents a constant acceleration, right? So it's just going to be a constant number, which is not going to change or vary. So this gives you the slope of this velocity time graph gives you a constant acceleration. So is there any question up until this point?
No.
All right. So now the same case you can do yourself, or let me know if you want me to do it. Is it okay for everyone? You understand how would be the negative acceleration or the deceleration? Just tell me, for example, if I have a graph, velocity time graph, this is my velocity time graph, what line would be showing me negative acceleration? Or what kind of a slope I should have on this graph that shows me negative acceleration?
A downward slope?
Yeah, exactly, right? So the slope would be like this. So this corresponds to a negative or negative acceleration, or also known as deceleration. Now, the interesting thing happens if I have a graph, velocity time graph, which is like this, and I see some curves on this graph. So for example, this is a curve. What is happening over here? Anyone? In terms of both velocity and acceleration? Well, if you give me the answer for acceleration, that would be giving me the answer for velocity as well. So
both velocity and acceleration are increasing with time.
Right. See, exactly. So velocity is also increasing, and so is the acceleration, right? Because if I see at this point and at this point, we have two different values for velocity, and v2 is greater than v1 again. So definitely velocity is increasing, we can tell. But if you look at the slope at every point, now we know for curves, the slopes are the tangent lines at these points, and then you can find the slope by picking another point on this tangent line, and then you can find the slope in the same way. So you'd get change in velocity divided by change in time. Suppose for this tangent, let's call it tangent 1. So for tangent 1, you would get something, a value for acceleration, which would be smaller than the change in velocity by change in time if I do it at this tangent, right? This one. So if this is tangent 2, which means that at 2, the change in velocity by change in time has increased, which means that the acceleration is increasing. So is that clear for everyone?
Yes.
Okay, great. So if that's clear, you'd also understand the same concept for decreasing acceleration, right? So I'll just quickly draw the graph, and the decreasing acceleration would be a graph that looks like what? Like this, right? So at this point, there is some value for acceleration. You can just draw this tangent, And at this point, you can see the tangent has sloped downwards. This is not it. Just let me draw it again. So it's sloped downwards now, right? So slope has decreased compared to this tangent one, and hence the acceleration has decreased because the tangent is really telling you about the slope of the graph. So is everything clear so far?
Yes.
Okay, good. So with this now, we can move on to the next topic of acceleration due to gravity, right? So does anyone have any idea about this sentence or this statement, acceleration due to gravity? What I mean is, what comes to your mind when you hear this thing, acceleration due to gravity? Okay, so really what it is, for example, you have a mass. What happens is, I'm not going to go into much details of this thing right now, because that's not required for you, but you have a mass, any mass, suppose it's a mass, it's the earth, right? Or it could be the sun, or any mass that is really heavy. So let's say that this is capital M. Whenever you have a mass, what it does really, I'll tell you what really happens is that it bends the space-time fabric, right? And when it does that, it is going to produce this effect of gravity. So again, I'm not going to go into more details. I'll try to explain. Of course, even when you're doing in A levels, you will not really see this type of things, bending of space-time and everything. You will talk in terms of Newtonian gravity, right? And the Newtonian gravity is simple. It tells you that if I have two masses, they will experience a force of attraction, and that force of attraction is going to be minus gm by r squared. Now, if I have another mass, suppose this capital M is the mass of the sun, and this small m is our earth, right? So I'll just write it down as well. So this is sun and this is earth. And suppose that the separation from the centers of these two planets, well, earth is a planet and sun is a star, is some r, right? Now, what happens here is that the earth is going to experience a force of attraction, which is what we call gravity. Now, Newtonian perspective is that you don't know what is causing this gravity. You just know that there is going to be some force of attraction between these two masses. You don't know what is causing it. And in Newton's Principia of Mathematics, where he wrote all these things down, he said that this topic, that to understand what is causing the gravity, is left as an exercise to the reader, right? And so Newton himself did not know, but he gave us this expression for calculating the force, which is pretty accurate for most of the time, right? So what happens is that the earth is going to be attracted to the sun. And of course, if there is a force of attraction, there should be acceleration, right? Everybody agrees with that?
Yes.
Right? So because that's simply because we know that force can be written as really the
Excuse me,
sum
sir.
of all the forces.
I have one question.
Yeah. Yes. I'm sorry. Someone said they have a question, right? Okay, I cannot hear you. If you have a question, feel free to stop me again and ask the question. Till then, I'll continue. So we know that a force, sum of all the forces, is defined as the product of mass times acceleration, which means that if I exert a force on any mass, if I push or pull a mass, then that's going to produce some kind of acceleration in that object, really. So of course, if there is this force of gravity between these two planets, then there should be some acceleration. So Earth is going to be pulled, you can say, towards the sun with some acceleration.
Excuse me, sir. May I ask you one question?
Yeah, I cannot hear you. Can you please repeat?
May I ask you one question, sir, regarding this study?
Yeah, sure. Ask your question.
Am I audible?
Yeah, I can hear you now. I can hear you. Can you hear me? Hello?
Hello? Hello?
Yeah, I can hear you. Can you hear me?
Yes, sir. Sir, I have one confusion regarding the here capital G and small g. We know that small g is acceleration due to gravity. And
Exactly. So
capital,
I'm coming to that. Yeah.
capital G is universal gravitational constant. So
Yeah,
it's a
this
bit
capital
different
G is, yeah.
small g. That
So
capital
I'm coming
G,
to the I'm coming to the small g, which is the acceleration due to gravity, right?
yes, sir.
Yeah. So I did not understand your question. What's your question again?
My question is, yes, sir, you are just describing acceleration due to gravity. That we understand that that is actually small g. There is the attraction force by the center of the earth. And here capital G, so far I know that it is universal gravitational constant. That is actually here the equation we have written F equal to G M1 M2 by R square. That is for the sun, moon. I mean any two objects, even then in the earth or outside the earth, can attract each other. That is gravitational force there. Acceleration due to gravity, I think that a bit different from that. So can you please clear this concept accordingly?
Yeah. So basically, I was writing the expression for force, which is going to give me the expression for acceleration due to gravity. Of course, I could have written it directly as G is equal to minus Gm by R squared, which is the expression for acceleration due to gravity. And then what you do is you put in the radius of the Earth over here, and you put in the mass of the Earth, and this gives you approximately 9.81 meters per second squared, which is the acceleration due to gravity, right? But where do we come? One of the ways that we can come to this expression is by writing down the force of gravity, right? And then we'll equate it with the this expression F equals ma. And once you do that, you get minus Gm m by R squared is equal to this thing, right? Because you can think like this, that these both are forces. And so if I do that, this gives me ma, where small m's cancel out, and this gives me acceleration as minus Gm by R squared, right? Now, we can use a change of variable, if you might call it that. Just say that this a is now some g, where g is the acceleration produced due to gravity, right? And that's why we are changing it to.
Can we just write one point G equal to F? We know F equal to mg. From that equation, we can write G equal to F by m. Is it, sir? F equal to mg. If we consider W weight equal to mg,
Yeah.
I mean that here W equal to mg, so G equal to W by m.
Right.
That,
Right.
sir, explain.
But that's not the fundamental way of, because how do you define weight? You define weight in terms of acceleration due to gravity, right? But
Yes.
yeah, so we've the goal of this topic was really to write down well, just to explain what acceleration due to gravity is, for O levels, we don't even need to think in terms of these forces and writing G as this thing. We just give a value to G as far as O levels syllabus is concerned, right? My point over here was just to explain where does this value comes from. And it comes from the fact, from the force of attraction between two masses. And then you can say that this force is responsible for some acceleration, and hence I can equate this to mass times acceleration, and then find the value of, or find the expression for acceleration really. And that acceleration, because this force is of gravity, then that acceleration is going to be that acceleration, which is going to, which is for the Earth, how Earth is being attracted towards the sun. So the acceleration of the Earth towards the, it would be the acceleration of any object that is going to be coming, you can say, on the surface of the Earth, right?
Yes,
That's
sir.
the
And
acceleration
then
due to gravity.
but so far I think that small g acceleration due to gravity, right, sir? It would be zero at the space and nearly zero at the
Oh,
space. And
I understand. I got your. I think I got what you're trying to say. You're saying, so exactly. You're right. It will not be zero in space. So
yeah,
you can say that in this distance, it will, of course, it will not be zero. But this acceleration due to gravity would be there on the surface of the Earth, right? On the surface of the Earth, for example, that's why when you jump, you come back to the ground, because you're going to experience this 9.8 meters per second squared pulling you back to the surface of the Earth. And so we get that by just substituting, because as you can see over here, when I equated these two expressions, the small m, now the small m in this case would be the mass of a person, for example, who jumps on the surface of the Earth, right? So I think the confusion here is that this diagram was completely separate.
Actually, I would like to just clear my concept here, that I would like to see the variation of values of g with respect to distance from the center of Earth to the space through the Earth surface. The values of g, how does it vary from the center of Earth to the surface of Earth to the space? In three, up to this three position, how the value of g varies. Here 9.81 in the Earth surface, but at the
On the surface of the Earth, it's 9.81. As you move away from the surface of the Earth, it will start decreasing, right? The value for g would start decreasing. Now, if you're at this, yeah,
yes,
with this thing, with this, it's known as the inverse square law. I'm not trying to get into these things because, again, these are not the topics for O levels.
With respect to distance from the center of Earth to the space, how does it vary actually, sir? I would like to see it.
Oh, you mean you want me to? You're asking for a graph between this thing. You can say distance and the acceleration of gravity.
G versus R. Yes, yes. G versus R. G along y-axis, then R along x-axis. This plot I would like to see, sir.
Oh, you're saying you would like to see this plot for? Yes. Okay. I mean, it's not in the syllabus for O levels. You're not required to know how would acceleration due to gravity change as R changes, right? But the graph looks something like this, that yes, from the center of the Earth, the acceleration due to gravity, it's going to increase like this, right? So it looks, it increases, and the acceleration due to gravity at the center is, at the surface is some value, which is 9.8 meters per second. And then it starts decreasing due to the fact of this inverse square relationship. And so as you move away from the surface, from the surface of the Earth, you start moving away into the space, then it starts decreasing like this, right? Which is 1 over
Yes,
r squared,
I
right?
understood. Thank you, sir. Thank you.
Right? Okay, yeah. I did not want to go into all these details because they're not the topic for O levels, right? Of course, if you're doing A level physics, A2, especially A2 physics, there in gravity, you see all of these things as well, right? So anyways, I think we went too far off topic. I'll now just quickly explain. So is this clear for everyone, by the way? Do you understand I mean, with this discussion, I think the concept of gravity, acceleration due to gravity, must have been clearer for everyone. Is there any question from anyone on this thing? Okay, so well, really so I'll just sum it up now. The acceleration really due to gravity is so for example, this is the surface of the earth, and you're here, you jump on the surface of the earth, you rise to some height. What will you will experience? You'll experience a pull back downwards to the surface of the earth, and that's why all things come back to the ground, really. And that's because you would experience some acceleration due to gravity. This acceleration is pulling you back towards the surface of the earth, right? So is that clear? That's really what you should be knowing up until this point. So it has a value which is 9.8 meters per second squared. So it's the modulus. So if you just ignore the signs, right? I'm just saying that you're ignoring the sign. You can, because it depends. You can take it either positive or negative. That completely depends on your choice of coordinate system. For example, if you say that if I define a coordinate system for this person as upwards is positive, and that then downwards would be negative, and of course acceleration due to gravity is pulling you to the center of the earth, which is downwards, right? So this would be minus 9.8 meters per second in that particular scenario. So that's acceleration due to gravity, and this is the value minus 9.8 meters per second. And this value is telling you that once you jump on the surface of the earth, you could think like this, you would be pulled back to the earth by accelerating 9.8 meters per second back to the surface. So one of the interesting thing about acceleration due to gravity is that it does not depend on the mass of your for example, if you're jumping on this earth, it doesn't matter how heavy you are. You could be 1 kilograms, you could be 100 kilograms, you're going to come back to the ground with the same acceleration, right? So this acceleration is independent of the mass of the, so this person, really. We use different terms. We use test mass and source mass, but I don't want to go into that either. So is this clear? Is the understanding of this minus 9.8 meters per second clear for everyone?
Yes.
Right. Okay. And so the other thing to take away from this topic is that this acceleration due to gravity is going to vary on different planets. So it's going to be different on, you can say, other planets. So it's not a fixed value. Minus 9.8 meters per second is not a universally fixed value. It's not that. It is going to change from different planets as you move on from planet to planet. And the reason for that lies in this expression that I wrote over here, that really G is, let's again ignore the signs, Gm by r squared, where this m is the mass of the planet. You can think in terms of planets. If you're talking in terms of planets, then this is the mass of planets. So for example, I need to compute this value for moon, for the surface of the moon, right? So I'll just put the value for a mass of the moon and in this r, I'd put the radius of the moon from the center of the moon to the surface of the moon, and it would give me some other value. Now, because I think there is less time remaining in the meeting as well, you all are aware of this thing that it's easier for you to jump on the moon, right, compared to the surface of the earth. Is everyone aware of that?
Yes.
Yeah. So what's the reason for that? So I just want to see what did you, if you understood everything that we have been doing so far. Why, how come it's easier for you to jump on the moon and it takes time to come back to the surface of the moon compared to the same thing on the surface of the earth? Of course, you'd be thinking in terms of acceleration due to gravity, right? So why would you think that it's easier? Anyone?
Probably because of gravity.
Yeah, because of gravity, yes. In terms of this value, would this value be less on the moon or would it be higher? So the more this value is for G, which is 9.8 on Earth, right? So G on Earth is 9.8 meters per second squared. This thing is telling you the strength of gravity. So if there is more gravity, then of course you'd be pulled to the planet more strongly. If the strength of gravity is less, then you would be pulled slightly less strongly. And of course, if that's the case, then it would be easier for you to jump off the surface, right? So for moon, this is for Earth. So for moon, it should be less, right? The value for acceleration due to gravity should be less. And it is somewhere about 1.6 meters per second squared for moon. And of course, you can compute this value for different planets as well, right? At this point, I would also say that it's really fun to find these masses and a radius of different planets or stars and just compute the values and compare it with the value with the Earth. And it's a fun thing to play around with. Anyways, so this is more or less acceleration due to gravity, right? So after this, we should be starting the topic of air resistance, right? And I think we have 4 minutes remaining. So I'll try to cover this topic of air resistance as well. What comes to your mind when I use the word air resistance?
It is the force caused by air.
Yeah, well, more or less that's correct. So for example, that you're in a car, right? Suppose you're in a car, and I'll try to draw a car. Assume that this is a car, right? Who cares? This is a car and it's moving in this direction. Suppose it's moving with some velocity. Suppose it's 20 meters per second. I don't know, whatever. And of course, on Earth, we have atmosphere and there is air made up of oxygen, nitrogen, and different elements. So of course, there is some other medium as well. It's not completely empty. It's not vacuum, right? And because there is air, this car is going to be pushing against that air. Everybody agrees with that? Of course, you cannot see the air because the molecules are so small, but there is some air, and that's why air does not mean that there's nothing over there. There is air, and of course, if you have to move through that space, you have to push that air out of your way, and that's what this car has to do. It has to, if it has to move forward, it has to push the air in front of it out of the way, right? So of course, when it's doing that, this air is causing some resistance to this motion of the car, right? Because of course the car has to push that air out, right? So for example, if you're trying to go in a bunch of people, there are a bunch of people, there's a crowd, and you want to go through this crowd, normally you would see what should not happen, but it happens. You'd start pushing these people away out of your path, and you would want to reach the destination. So that's what really is happening. So you can think of these people as some air molecules, and the car is going to push against these molecules and it's going to move. So the fact that it has to push these molecules of air out of its way is giving rise to this air resistance. This was in terms of horizontal motion. Of course, anything that falls vertically, if it falls really, is always going to experience air resistance as well. So for example, think of an object, a ball, and it falls back to the ground or it rises upwards. Both could be possible. In both cases, this ball would be experiencing air resistance in exactly the same way as I explained in the case of this car, right? The ball, if it has to fall back to the ground, it is going to be pushing some air molecules away from its path, right? So it's going to push them, these molecules. So their molecules are going to move out of its way like this. And the fact that it has to do that is giving rise to this air resistance, which you can think in terms of a force that is acting on this ball. And of course, that force would be in the opposite direction to the motion of the ball, right? Because the force is trying to, you can say it is trying to slow down this object, right? It's going to slow down the object because, of course, when the object pushes the molecules, it is transferring some of its energy into these air molecules, which means that it's losing some energy, right? Is everybody following along, by the way?
Yes.
Okay, so I mean, if you think of these things more deeply, they're really interesting, and sometimes I tend to get lost and then I start explaining more than I should. Feel free to stop